All right, the next concept on this short video lectures is something called hybridization. Now, the first minute here is going to be all you really need to know, and you could probably stop lecture after this, but the rest of the lecture is going to focus conceptually on what it is, which might give you a deeper understanding of it. But for the most part, hybridization is this. Once you identify the number of electron domains, and this table is found on page 13 of your packet, okay? The number of electron domains, once you figure how many there are, if it says what is the hybridization around the central atom, you simply just match up the number of electron domains with the number of s and p and d potential orbitals that make up that number. For example, something has 2 electron domains. It is sp hybridized, always. So if there's 2 electron domains, sp. Think of the s as having a superscript of 1 and p having a 1. So if I added together 1s and 1p, that adds up to 2. If the numbers of s's and p's add up, they need to add up to the number of electron domains present. If it has 3 electron domains, sp2, which is s1, p2, 1 plus 2 is 3. If it's got 4 electron domains, sp3, 1s, 3 p's, that adds up to 4. Okay, if it gets to 5 or 6, again, it's hypervalent, and that's when we start seeing the d orbital pop in. There's an s, there are 3 p's, and there's a d1. 1 plus 3 plus 1 add up to 5, and 1s, 3 p's, and 2 d's equals 6. So once you identify the number of electron domains, the hybridization, you just simply need to match it based on the number of s's and p's and d's that add up to that number. So for example, up here, let's say here's your Lewis structure drawing. They might ask, what is the hybridization around the central atom X? First thing you got to do is figure out how many electron domains it has. A double bond only counts as 1, so 1 electron domain, 2, and any lone pairs counts as well. This guy has 3 electron domains, and so the element X would have sp2 hybridization. And that's, if they ask what is the hybridization of the element X, you'd say sp2, and that's it. Okay? And that's all you have to do for hybridization. So if you want to stop lecture now, you can. The rest of the lecture will focus on what it is. So first of all, if we draw the orbital notation of carbon, carbon has got 6 electrons total. So 1s, arrow up and down, 2s, arrow up and down, and 2p's always comes in 3s. And following Hund's rule, 1 in each, that gets me to 6 electrons. Okay? Now, whenever we draw the dot structure of carbon, we put 4 dots around it. 4 single dots, it wants to bond 4 times. Right now, if I were to look at this, it looks like the 2s is full, that there'd only be 2 electrons available for carbon to bond with. So what the heck's going on here? Why do we have 4 single dots? This would look more like that there'd be 2 dots on the s, and there'd be 2 sole dots on the p's, and therefore we'd expect it to bond twice. So what happens here? Well, what happens is in order to bond, we're looking at the entire second energy level total. So what happens is one of these electrons from the s's jumps up into the p's. And therefore now there's 1 electron into each. And this is why carbon ends up having 4 single dots, is that electron from the 2s jumps in the p, so there's 1 electron in each area. Okay? Now these are the affordable areas that we can now bond with. Okay? Now, if carbon is going to do the molecule CH4, if I were to draw the Lewis structure, how many electron domains does it have? Hopefully you said 4. It has 4 electron domains. And therefore, it would have sp3 hybridization. What does that mean? Well, that means that the 2s, one of the s's, and all 3 of the p orbitals, they all hybridize together. So the s orbital is shaped as a sphere, and these p orbitals are shaped as dumbbells. Well, these 2 guys come together, and they morph, and they create one like orbital, which has s and p characteristics together. And what it usually looks like is this, where it's got still the circular head of the s orbital and a lobe part of the p, and this is called an sp3 orbital. It can also be an sp2 or sp, but an sp ends up having this shape of where we have this dual nature of both of them morphing together. So we end up creating is 4 identical orbitals that are all sp3. And this is what hybridization is that now when I bond, these are 4 identical orbitals. Okay? If it wasn't, I'd be bonding to a 2s and 3 2p's, and those would cause different energy values because an s orbital is different energy than p orbital. So one bond would be weaker than the other 3, and that can't happen. So hybridization is where these orbitals come together and they create one specific orbital of equal energy, and it depends on how many that are morphed together. And right there is an example of hybridization. So now carbon, with its 4 sp3 orbitals, are here, where we have 1 electron into each. Well, now hydrogen will come over and overlap in this zone. So we have is the hydrogen has its electron in 1s orbital. So all 3 of these areas, we have the hydrogen's 1s with 1 electron, and one of the carbon's sp3 orbitals with an electron. They overlap, and now these electrons can swap back and forth between them, fulfilling that orbital. If this electron rotates up, now there's 2 electrons in the 1s for hydrogen. If this electron rotates down, now there's 2 in that sp3 orbital, and the molecule is sharing electrons. And that sharing is occurring between the 1s of the hydrogen to the sp3 of the carbon, and every bond has that same exact alignment of those orbitals, and therefore each bond is of equal energy. So that's what hybridization is. Hybridization is the s and p orbitals creating one like orbital, that is then going to bond so that each orbital is of equal energies. When we get to 5 and 6 domains, not only are we bonding now an s with a p, but now also with a d. So these orbitals all come together. For number 5, it's 1s, it's 3 p's, and 1 of the d's, and they come together and they morph and create one hybrid orbital of equal energies that bonds whenever something is hypervalent. And then if it gets to 6, then it's just another d orbital, and again it morphs together to creating one orbital of equal energy for all those areas to bond with, and that's hybridization.